I'm Gary McNeil, Communications Director for EPA's Combined Heat and Power Partnership. The CHP Partnership is presenting this webinar in cooperation with the Combined Heat and Power Association. The CHP Partnership is a voluntary program that promotes increased deployment of efficient CHP systems which help reduce emissions of carbon dioxide and other air pollutants. We offer information and tools to support project development, and we work to put in place emissions regulations and permitting practices that recognize the emissions avoiding value of CHP. Please visit our website and please consider joining the partnership. Most of you are probably familiar with the LEED rating system. The LEED Green Building Program launched in 2000, and as of July 2015, there are more than 23,000 LEED certified commercial projects representing 3.3 billion square feet. From the graph, which includes both certified projects and projects which have registered to begin the certification process, you can see the explosive growth in LEED projects since 2000. The types of buildings being certified, which include office, education, residential, and healthcare, can all be great fits for CHP, and there are many successful applications in these sectors. Before the presentations begin, we'd like the audience to respond to the poll questions on their screen. Please select all the answers that apply to you. Once we have a good response, Sarah will close the poll and share the results live. The webinar will start with a summary of what we have learned over the past year, working with the CHP industry, the U.S. Green Building Council, and others in the green building community to better understand how CHP can help new buildings achieve LEED certification. Recent advancements in CHP systems have made CHP a good candidate for building types that may not previously have considered CHP. These advances include remotely operated systems, modular drop-in systems, third-party ownership models, and modern absorption chillers. Our speakers today will be talking about all of these game changers. Now I'd like to introduce the speakers. Charlie Goff is an engineer at Eastern Research Group, a multidisciplinary consulting firm. Mr. Goff has provided engineering and program management support to the EPA Combined Heat and Power Partnership since 2005. He has a BS in mechanical engineering and a master's in public policy with a focus on clean energy and environmental policy. He is also a LEED AP. Doug Davis works for Broad USA and has 25 years of experience in the sales, design, and installation of large chilled water systems and CHP. He has a BS in engineering from Purdue University. Diane Molokotos is a project engineer at Aegis Energy Services. She holds a BS in mechanical engineering and a master's of business administration. Jeff Biter has been in the energy industry since 1990. He acquired the Capstone product line in 2007 and has since grown his fleet to over 450 microturbines. Today, his company, Efinity, has over 100 small-scale CHP plants, making electricity, hot water, chilled water, or steam. All attendees will be sent a link to the slides and an audio recording, which will be posted on the CHP Partnership and CHP website. Thank you.
Okay, well, I guess I will get started. Thank you, everyone, for being here today. To kick things off and serve as a primer for some of the case study presentations that are going to follow, I'm going to provide an overview of CHP and LEED. Specifically, I'm going to touch on CHP's value for LEED projects, the mechanics of how CHP is treated in the LEED for building design and construction, new constructions and major renovations rating system, and discuss a couple of the CHP Partnership LEED resources that we've developed as part of our work over the past year. First, a couple of notes. My presentation focuses on LEED version 2009. The most recent rating system is LEED v4, but registration for LEED v 2009 is open until October 31st, 2016. So we think a lot of projects will still be using this system. Also, through our research, it doesn't seem that the way in which CHP is treated is changing between the two systems. Second, my presentation is going to focus on the LEED for building design and construction new construction rating system, and specifically when CHP outputs are used within the same building as the CHP system. The CHP Partnership, we also plan to explore how district energy is treated, as well as how CHP is treated under the existing buildings rating system, but that is work planned for later this year. So on this slide, you can see the LEED version 2009 certification levels. There are 4 of them. You can be certified silver, gold, and platinum. Buildings earn points in a number of categories and are awarded a certification level based on the number of points earned. In total, there are 56 credits worth a potential of 110 points. Next slide. One of these credits is the Energy and Atmosphere Optimized Energy Performance Credit, which is the credit most applicable to CHP. The intent of this credit is to maximize the energy efficiency of buildings. The credit is the largest point earning credit in all of LEED and is therefore incredibly important for LEED projects. Maximizing the number of points earned in this credit goes a long way towards a project meeting its LEED certification goals or even exceeding them. Under V2009, there are 19 points available on this credit. To earn all 19 points requires a 48% reduction in energy costs from ASHRAE 90 standard 90.1, or otherwise known as the baseline building, which I'll mention a little bit in the next couple slides. Achieving all of the optimized energy performance points would represent almost 50% of the points needed to become LEED certified. So you can see how important this credit category really is. Next slide. Yeah, so here you can see CHP has been proven to help projects earn a lot of points. One of our CHP partners calculated the point contribution of CHP for 8 buildings now in construction by modeling each building twice. One using grid-supplied electricity and an on-site boiler, and once using CHP. As you can see in this chart, CHP is helping these buildings earn as many as 9 points more than they would otherwise earn if they used grid-supplied electricity and an on-site boiler. We've also seen CHP help projects earn up to 14 points that they otherwise would not have earned. So you can see how important CHP can be for LEED projects. Now, one thing to point out is that every project is different, and the impact CHP will have is dependent on building-specific variables, such as the performance parameters of the specific system, how many hours the system runs, power-to-heat ratio, and the useful power and heat outputs relative to the specific building load. Next slide. So as I mentioned, the credit category where CHP has the biggest impact is the Optimized Energy Performance Credit. Under this credit, project teams have 3 options for earning points. Options 2 and 3 are not really applicable to CHP. They involve implementing prescriptive measures outlined in ASHRAE Advanced Energy Design Guides. So CHP doesn't really help a project earn points under either of these options. Option 1, however, involves running a whole building energy simulation using an energy model of a baseline building that meets the prescriptive requirements of ASHRAE 90.1 2007 and BEACH 2009, and another model for a design building that includes all of the energy efficiency measures that a building plans to implement, which would include the CHP system. So in case, for people who aren't aware, ASHRAE 90.1 establishes minimum requirements for the energy efficient design of buildings and provides prescriptive measures that define the minimum efficiency of things like building insulation, HVAC efficiency, etc. Meeting these prescriptive requirements is what establishes the baseline building for the purpose of comparison in the LEED calculation. So using option 1, the design building must demonstrate a minimum of 10% savings in energy cost compared to the baseline building. Anything over a 10% savings results in points earned on an incremental scale based on the savings achieved. So more points are awarded as energy cost savings of the design building increase compared to that of the baseline building. So the key point here is that points are awarded based on energy cost savings, not on energy unit savings, such as BTU. This has implications because implementing energy efficiency measures, including CHP, that reduce purchases of grid electricity in high-cost areas is more beneficial for earning points than reducing purchases in areas with cheaper electricity rates. So next slide. So what are some of the specifics related to how CHP can help earn points in LEED? USGBC has published a methodology that provides an overview of how CHP should be treated in the whole building energy simulation, which is option 1, which is what I just discussed. So it applies to on-site CHP, which can either have the same ownership as the project or different ownership. This is important because buildings that enter into third-party ownership arrangements for the CHP system can still earn points that the CHP system generates. They don't need to own the CHP system to get those points. And this is something that Diane's going to touch on during her presentation in a little bit. Next slide. Basically, there are 3 steps to the methodology. First, the energy requirements for the baseline building, which is the one that meets the ASHRAE 90.1 standard, are estimated using the energy model, and based on the model output, energy costs are calculated. Next slide. Second, the same process is followed for the design building, the one that includes CHP, as well as any other energy efficiency measures that the project plans to implement. So the key here is that the design building with CHP only needs to account for the cost of fuel used in the CHP system, as well as any residual utility electricity and supplemental thermal needed by the building. The electricity and thermal outputs from the CHP system are considered free in the energy cost comparison, which is important. Next slide. So finally, points are calculated based on the percentage energy cost savings of the design building compared to the baseline building. So in this table, this is a sampling of the points awarded for various percentage improvements under LEED 2009. And you can see that as the percent energy cost savings over the baseline increase, more points are earned. So the key behind CHP's ability to earn points is its enhanced efficiency over separate heat and power, which is the purchased utility electricity in an on-site boiler. CHP systems typically achieve total system efficiencies of 60 to 80% compared to purchased utility electricity in an on-site boiler, which is approximately 50% when you combine the two. Increased efficiency means less fuel and thus energy cost savings. Also, by producing on-site power, CHP reduces purchases of grid electricity. Purchasing natural gas, which is the usual fuel for CHP, is typically cheaper than buying grid electricity. Thus, you get cost savings. Next slide. So over the course of our work from the past year, we've developed a couple of resources to help LEED project teams better understand CHP, its benefits, and its impact on LEED projects. The first is a fact sheet or white paper that introduces CHP and its benefits. It talks about the LEED building design and construction rating system and how CHP fits in. It touches on some of the things I talked about over the past few minutes, as well as some other things. The second resource is a LEED CHP calculator. This is an Excel-based tool that estimates the energy cost savings and optimized energy performance points a building can achieve with CHP. So it's something that's supposed to be intended to be used at the very early stages of building design to give project teams an idea of the energy cost savings that can be achieved with CHP, as well as the potential points that a CHP system can help earn a project. The next slide. So that about covers it, but I'd like to finish with just a few takeaways that we think is important to leave everyone with. First, CHP can have a dramatic LEED point impact. We've seen projects earn up to 9 to 14 points with CHP compared to separate heat and power, which is really significant given that you only need 40 points to become LEED certified. Second, CHP has lots of other benefits for buildings. You get energy cost savings, environmental benefits, enhanced power reliability. So getting these extra LEED points is really a bonus. I mean, you're really going to want to implement CHP for a number of other reasons besides just getting LEED points. We also hope that for your next LEED project, you think of CHP from the outset as a potential energy strategy. It requires some planning and investment up front, but the benefits to a building owner can really be big. Finally, we at the CHP Partnership are here to help. We have lots of tools and resources concerning CHP, including the ones I just went over specific to LEED, as well as a partner network of CHP professionals. So I'd really encourage you, if you have any questions or would like any assistance in better understanding how CHP fits within the LEED rating system, to please contact us. And my contact information is on the next slide, as well as how to contact the CHP Partnership. So if you have any questions, feel free to contact us at either of these ways. And that's it. I will hand it over to Doug now, who's going to talk about modern absorption chillers. Thank you.
Thanks, Charlie. That was great. So good afternoon, everyone. My name is Doug Davis. Can be reached at the contact information shown. Before I get started, though, I would want to maybe circle back to what Charlie indicated. The CHP Association is actually having our annual meeting on September 14th, and we are an open membership committee, so we welcome everyone attending and perhaps even considering joining the association this year if you haven't already. The next 10 minutes or so, we're going to talk a little bit about how modern absorption can make CCHP simple to integrate and design into your HVAC systems. So to begin with, I thought it'd be good to kind of state what an absorber is. And basically, an absorber is a thermally driven chiller that makes cold water. Typical application range for the chill water is about 44 degrees F Fahrenheit and is usually adjustable a couple degrees in both directions. Commonly, absorbers have been applied in buildings for almost any type of facility, ranging from schools to universities to hospitals, offices, retail, and data centers. We are seeing a big growth in the CHP market. I'd say about 70% of absorption sales today is tied to some form of heat recovery or combined heat power projects. Absorbers have been around for a while. They're also known by a couple other names, such as absorption chillers, or perhaps if a machine is actually burning natural gas directly, people often refer to them as chiller heaters, since they not only produce cold water for air conditioning, but they can also create hot water for heating a building or even domestic hot water. Lastly, I was hoping to just touch lightly on what's new about modern absorption units. I say over the last decade or so, the efficiency of the technology has gotten substantially better than it was in the past, and also its ability to unload quite efficiently. Today, with an HVAC application, it's really important for machines to be able to unload from 100 down to 10% as the load profile in the building changes. And lastly, in general, we've seen a lot of uptick in higher grade materials and tube thicknesses and shell thicknesses, much more robust programmable logic controllers that control the machines, as well as higher vacuum standards. One of the key success factors of an absorption chiller is its ability to maintain a vacuum, because the way these machines work is they actually work well below atmospheric pressure. So practicing what we call vacuum management is really critical to the long-term longevity of the machine, as well as its high operating efficiency. Next slide, Sarah. So absorption has been around for almost 70 years now. This technology was actually pioneered in New York State, and what we're hoping to show here is just a couple pictures about how the technology has changed in the last decade or so. Modern absorbers today are about 40% more efficient than they were 15 years ago, and as you can imagine, information technology has really transformed this technology into a much more user-friendly chiller, in the sense that modern controls and using the internet to actually watch these machines remotely really allows the operation to be demystified, and it's kind of simple now for almost anyone, even with a very basic understanding of chill water operation, to be able to diagnose and troubleshoot machines should they need a little bit of TLC. Next slide. So a little bit about our company. Broad is a manufacturer of absorption chillers. We also monitor these machines for life and provide service and training on absorbers. Currently, we have machines operating in around 80 different countries, and starting from the green campus on the right there, that's actually our manufacturing facility in Asia, where all machines are built and actually tested before they leave the factory at the customer's conditions. The picture on the lower left shows our monitoring center, and then the blue bars across the upper left are basically different models of absorbers, starting with gas-fired machines, or steam-fired machines, or exhaust-fired machines, or hot water-fired, as well as both two-stage and single-stage machines. What really is truly novel about absorbers today is they can actually handle up to 3 different thermal inputs, which really makes them ideal for combination heating power applications, where you might have various different forms of waste heat that need to be recovered and utilized in air conditioning. Next slide. So to highlight why modern absorbers are good for LEED projects is many building designs have traditional heat loads that can make CHP effective, but depending on where the building is located and the time of the year, many commercial office buildings or hospitals sometimes will have a dramatic drop-off in heating requirements in the summertime. So by basically turning cooling loads into thermal chillers, you can basically turn cooling loads into heat loads, which will allow you to really recover that waste heat off of power generation and drive the energy back into the building in a useful purpose. As far as LEED points, there is one easy layup to get one LEED point even without CHP, and that's to consider designing a building with no chemical refrigerants. The LEED rating system basically allows LEED points by eliminating the use of HFCs or HCFCs, and there's actually an organization out there that's been quite effective at sharing a lot of the attributes of some of these modern or natural refrigerants, such as water, which is actually the refrigerant in the absorption chiller, or CO2 for low temperature systems. So if you haven't had a chance yet, I'd encourage you to look at their website and learn a little bit about what a lot of companies are doing today with regard to trying to get away from chemical refrigerants. Next slide. So in most combined heat power systems, the jobs generally begin with the selection of a prime mover. And depending on the type of prime mover you're going to design your system around, you'll have various forms of waste heat. But the key factor is all of these different forms of waste heat can be used to power a modern absorber. So one of the new prime movers that we're starting to see some traction with in North America are fuel cells. And not all fuel cells, but some fuel cells, as a byproduct of a chemical reaction, actually generate hot air around 750 degrees, which is more than enough heat to power a two-stage high-efficiency absorber. Another popular choice for prime movers are turbines, both large or small, sometimes referred to as microturbines. And again, the byproduct of the combustion of natural gas is going to generate sufficient heat to power usually a double effect absorber, or perhaps you can convert that waste heat into steam or hot water and then elect to choose either a single or a two-stage absorber. Also, reciprocating engines by far seem to be a very popular choice still in the combined heat power industry. And just like the car you drove into work today with, you have both tailpipe exhaust and what's commonly referred to as jacket water, which really keeps the engine block cool. So again, typically the exhaust temperature off the tailpipe might be 800–900 degrees, and the jacket water usually somewhere around 200 degrees, both of which are sufficient amounts of heat to power a modern absorber. So to kind of summarize, by looking at thermal chillers, you can often use the waste heat in cooling operation and will sometimes actually add to the size or the capacity of the combined heat power system, because you'll be able to utilize the waste heat on months where the heating load might actually fall off. Next slide. So the first job we thought we'd highlight today is actually the first project that we've been involved in that ended up getting LEED Platinum certification, or 4 green globes as well. And this is actually a big box retail store. They're a national chain that specializes in organic foods, and basically you'll see some photographs here kind of summarizing that from a design standpoint, the store wanted to do a couple tasks. One was to basically have the ability to run the store with or without the electric grid. They've had a lot of power losses in different facilities in the Northeast, and for their standpoint, it was really important to have a store be very resilient to make sure they're actually able to serve the community when the grid does go down. They actually ended up selecting, from a HVAC standpoint, a chiller heater arrangement, which essentially meant they had 2 boxes in the mechanical room, and both of those boxes were natural gas-fired chiller heaters, and one of those boxes ended up being what we call a multi-energy unit that actually recovered the waste heat off a reciprocating engine. Just some rough numbers or rules of thumb, about 70 tons of free air conditioning is able to be put back into the store by running essentially 150 kW reciprocating engine. And then in the wintertime or in the summertime, the store is either looking for chill water or hot water, as well as continuous domestic hot water. So basically the first stage of heating or cooling the space is to utilize the free energy, and when the load exceeds the amount of free energy we can recover off the cogen, the natural gas burner on the absorber would basically carry the work of additional capacity. Also showing, the sizing of the CHP system needs to be looked at not only during the daytime, during the peak load when the store is occupied, but also in the nighttime when the store is shut down, but there's still
minimum needs for electricity and low temperature refrigeration systems. Next slide. A couple other pictures of the schematic of the store. During construction, actually Hurricane Sandy struck, and the parking lot was actually filled with water. So the designers on the design team that elected to put all the mechanical systems on the roof turned out to be a really, really great decision. The store also combines a lot of other great energy savings technologies, such as photovoltaic and rainwater capture systems, which also, I think, was able to push them to the LEED Platinum certification. One of the interesting things that happened last summer was the photovoltaic system would actually generate more power than people were anticipating. So again, there was times during the year that they would actually shut off the engine because in this particular part of New York, you're not allowed to export power to the grid. So during those days, the operator would make the decision to actually turn off the engine for a few hours while the photovoltaic systems was able to give them more than enough power to power the store. And again, the flexibility of not having to have a complicated sequence of operation made the turning on and off of the cogeneration system pretty much invisible to the HVAC plant. Next slide. So just some quick benefits of perhaps some advantages of looking at absorption from a chill water standpoint. In this particular case, the mechanical room was probably much smaller than it would have been for a conventional boiler and regular chiller plant. Of course, there's also a lower cost to recover the waste heat by combining the heat recovery unit into what we would normally refer to as just a chiller heater. A much more simplified sequence of operation. They actually don't have an operator that runs the plant, but they do have people that periodically check on the performance of the system. I think a lot of big, catchphrases in the combined heat power industry today is uptime, and certainly by reducing the amount of moving parts on the system, theoretically the points of failure go down, which can theoretically increase uptime. Also, by using a combination of multi-energy absorption with the cogeneration, it really allowed for the loading of the chiller from either 10 to 100% and the redirecting of those waste heat streams into the four-pipe heating system or chill water system. Actually, one of the other neat things about this store is they're using CO2.
Excuse me, we're running out of time. We need to wrap up right away. We're a couple minutes over. Sorry.
Okay, sure. So I guess indirectly, as Charlie had indicated, the LEED point system allowed for a much more efficient use of the waste heat. Next slide. So this slide just shows, again, a system that's kind of similar in the sense that it's using steam. That's probably the one thing an absorber can't do, and this is in a hospital environment. It also shows an example of third-party ownership that Diane will continue on with the rest of the presentation. Thanks so much.
Hello, this is Diane Molakotos. Thank you for inviting me to contribute to this webinar to share with you Aegis's experience with 2 clients which have deployed our CHP systems to reduce energy costs and earn LEED points. But first, let me briefly tell you who we are at Aegis Energy Services. Next slide, please. We are a large developer of small modular CHP in the Northeast and Mid-Atlantic states, having installed over 500 CHP systems. Aegis is a NYSERDA qualified vendor and an EPA CHP partner. The company is vertically integrated from engineering, manufacturing, installing, maintaining, and often owning and operating systems. This structure provides single source responsibility and accountability to its clients. It's a privately held company headquartered in Massachusetts. It's been in business for over 30 years. Next slide, please. Here is a 75 kilowatt system. You can see from the size that we are indeed speaking of small modular systems. In addition to an induction system, Aegis has 2 types of synchronous systems that are black start capable, which simply means that these systems can continue to operate during a central power grid failure. Next slide, please. This is the basic architecture of our products, which are natural gas-driven reciprocating engines. In red are the basic heat recovery components. In green are the connections we use to interface with the building. I want to call attention to the red circled outputs of the system, which are highly valuable electricity and thermal energy. When comparing the total BTUs of these outputs with the natural gas input BTUs, the efficiency can be 80+%, which should be contrasted with the 30% efficiency of a central power plant. Next slide, please. Our CHP systems are modular and scalable, which means they can be used alone or combined for use in larger applications. Sizing the system for thermal loads and electrical loads requires proper sizing for maximum efficiency and savings. With small modular systems, there is no need to purchase and install something that doesn't fit or is oversized. Consistent with plug and play is the fact that most of the system and connection are pre-built in the factory, such as the pump and load modules, making installation relatively quick. These units are equipped with microprocessors and are IP accessible, which allow them to be remotely monitored by Aegis at its headquarters, thereby allowing for very high run times and capacity factors, making sure that the promised energy savings are achieved. This monitoring allows for independent operation, not requiring any building resources. Lastly, Aegis provides a comprehensive maintenance program, thereby ensuring long system life and uptime. Next slide, please. Since not every building is a good application for CHP, although many are, these are the characteristics that make a site a good fit for CHP. These characteristics make CHP a great technology for multifamily buildings, hotels, hospitals, nursing homes, health clubs, all of which are our clients. Next slide, please. Here is a quick review of the guiding principle of CHP design for maximizing energy savings. As discussed earlier, the value of CHP lies in its high efficiency, which stems from use of the waste heat from the engine that the engine produces. Therefore, in order to maximize this efficiency, the system is best designed to be thermal load following as shown. Aegis initially sizes an overall CHP system to match the building's thermal needs. It employs hot water storage tanks for peaks. The CHP modules are adjustable, have variable speed in order to match the building heat and hot water. If the thermal demand drops below that level, the system pauses to avoid heat dump. The only time there's a heat dump is if the building is performing electric peak shaving. Next slide, please. Let's start with the first of two case studies that I wish to present. The first is the case study called the Larstrand in New York City, which is a 184 residential unit and retail space building, 200,000 square feet with 24 stories, consisting of market rate and affordable rental apartments. This building is in its final stage of comments, awaiting silver certification. Aegis worked with Dagger Engineering, which was an engineering firm that helped design this building. Next slide, please. After reviewing many different options for energy savings and employing some building envelope and other strategies to earn the minimum energy credit of 1 point, Dagger and Aegis performed a feasibility study showing building thermal demands and electrical demands versus CHP output. That study pointed to a strong argument in favor of CHP. Subsequently, Aegis engineered and installed the CHP plant as shown, with one Aegis ThermoPower TP75 kilowatt unit, which provides 100% domestic hot water and 20% of the building's electrical needs. The estimated 12% energy cost savings provided 6 optimized energy points using an eQuest DOE2 modeling program. Next slide, please. Here's a worksheet that Dagger gave us showing the actual point contribution that CHP earned towards the overall certification. Essentially, they earned 1 point in the minimum energy credit by saving 12% over the baseline building by employing building envelope and other strategies. Then, post-CHP, the building saved an additional 12% using CHP. This combined 24% gave them an additional 6 points under the optimized energy performance category. Next slide, please. In speaking with the engineers at Dagger and the building developers, we gathered these lessons learned. First, that feasibility studies are paramount to success. and that proper CHP sizing results in high efficiency and high energy cost savings. CHP is a valuable source of LEED points, and the large strand goal was primarily energy savings and efficiency. LEED was a secondary goal. Next slide, please. Let me take a break here to briefly discuss some financial support for CHP projects. Many of you are aware of the incentives given to solar and wind, but you may be surprised that CHP has also support from local, state, and federal governments as well as utilities. Here is a small sample of what is available. Next slide, please. In order to locate various sources of funding throughout the U.S., we have found that the EPA CHP Partnership website has valuable information in general for CHP. In order to find funding, you should visit the URL given here. Next slide, please. As an alternative to owning a CHP system, a building may opt into a third-party ownership agreement, such as one presented here. The next case study I will share with you engaged in one such agreement, which essentially allowed them to earn LEED points with zero capital investment or any ongoing expenses. Next slide, please. This case study is a building called 315 on A, which is located in Boston. And as I said, this building employed a shared savings agreement with Aegis, as was previously discussed. This is a 255,000 square foot building, multifamily, completed in 2013, and has been gold certified under the V2009 LEED system. The heat in the building is an operating expense and is not prorated back to the tenants. Next slide, please. A feasibility study was conducted early on here also and rendered support for CHP as a good fit for this building in order to reduce energy costs. The plant consists of an Aegis thermal power 75 kilowatt system. It provides 100% of the domestic hot water heating and 80% of the building heat. The system provides 28% of the building's electrical load. The CHP system earned 4 of the 8 points under Optimized Energy Performance Credit, very similar to the previous case study I presented. Next slide, please. According to the building developer, here are some lessons learned from this project. First, that shared savings agreement avoided any risk for the developer and provided no cost LEED points to the building. As was the case before, energy savings was the main driver for CHP, not LEED points. And the developer saw that as the system efficiency, as the occupancy of the building grew, so did the system efficiency and savings scale up as well. Next slide, please. Some parting thoughts. CHP is a highly efficient and proven technology, thus resulting in major savings potential for building operating costs, provided that the systems are designed to be thermal load following. These savings present an attractive opportunity for LEED points and LEED certification for architects, developers, and new generation building tenants who expect to live in LEED buildings. As mentioned earlier, these LEED points from CHP must be considered early on in the design process. Financial support opportunities exist for CHP in the form of grants, incentives, and third-party ownership, and building owners and developers value sole source accountability vendors. Next slide, please. Up next, we have Jeff Biter. Thank you very much. Look forward to your questions.
Good afternoon, everyone. Jeff Biter here from Efinity, and I'm going to give you a brief presentation on the Pennsylvania State Employee Credit Union, which is otherwise known as PSECU. The facility is located in Harrisburg, Pennsylvania. The company, well, let me just say the CEO and the company were committed to doing a LEED building, and they serve several 100,000 members, 400,000 members, and is one of the largest credit unions in the state of Pennsylvania. They constructed a new headquarters building. It's very modern. It has all of the LEED attributes that you'd need. It's 239,000 square feet, and it enjoys a LEED Gold status on a 47-acre campus. They, again, have 400,000 members. Next slide, please. In 2011, PSECU realized it was time to invest in natural gas power generation, obviously benefit from shale gas in the Marcellus region not far away. and they incorporated that into their overall cost of operation and become more environmentally efficient. They turned to us with an interest in the Capstone microturbine for a combined cooling, heating, and power system solution, and that overall solution contributed 8 points to their LEED certification. Next slide. It took about 3 years of schematic design and development to sort of put the picture together for the combined heat power portion. Alan Bruner, the project manager at PSECU, was committed to the project along with the CEO, and Pete Spicer, the facilities manager. You need that commitment in any CHP project to have those champions to move a project forward. The plant was started in October of 2013. It's one of 352 buildings in the state of Pennsylvania that holds a gold certification level. Next slide, please. Requirements for the system. PSECU was looking for reliable on-site electricity, space heating, cooling, and chilled water. They teamed with us and UGI Performance Solution, a local energy services company, to develop the generation solution, and that utilized the Capstone natural gas-powered microturbine. And in their case, it was a C800, which I'll speak to. Next slide. The certification optimized the performance of the building that generated approximately 37% energy savings due to the on-site cogeneration system. Next slide, please. The system is comprised of really just 3 components. It's the Capstone turbine, C800 dual mode microturbine as the prime mover, and has 3 separate C200 modules in there that allow the unit to scale up or scale down depending upon the thermal priority need of the building. The engine will run all year long, with even during maintenance cycles, because you only shut one of the 200s down at a time. So the client will enjoy thermal and electrical production 24/7. It also adds to the 999 available reliability. The turbine exhaust is then pushed over to a diverter valve that will divert to either a 250-ton exhaust-fired absorption chiller, or simultaneously divert to a 4 million MMBTU hot water heat exchanger. So the client, depending upon what the building automation system is calling for, hot water, chilled, or hot air or chilled air, the client has the turbine will deliver air to the heat exchanger and to the absorber simultaneously to meet that demand. And that operation is controlled through the MTIM, the PLC control system. So the installation got completed in 2013. We handed the keys over to Pete Spicer and his operations team. Again, 3 components, a very small modular footprint: a turbine, an absorber, and a heat exchanger. Next slide, please. Quick snapshot of the flue gas fired absorber. Pretty decent sized footprint. I would say it's approximately 12 feet high, 8 feet wide, probably 10 feet deep. The heat exchanger is approximately 8 feet high, 6 feet wide, 6 feet deep. So again, very small modular footprint, and we've seen the ability for the Capstone to make hot water and feed that over to a hot water fired absorber, or to make flue gas and feed the flue gas to a flue gas fired absorber, and a flue gas benefit heat exchanger. So the options exist for hot water fired absorption, steam absorption chillers, and flue gas fired. Next slide, please. So the system, again, is operating. It provides standalone clean power for their data center. So, well, it also operates in dual mode, which has the ability to communicate with the utility grid. If it senses a voltage sag or a utility anomaly, the unit will open up and open a breaker and disconnect and island the site into an island mode and continue to operate. Turbines never shut down. Turbines merely take the command and go into isolation through the breaker, and then continue to produce electricity and thermal energy. That electricity, in this case, provides backup power to the data center UPS. And again, the thermal energy is for heating and cooling in the building. So through the Capstone remote monitoring program and service program, the customer decided to select a 9-year FPP. We call it, that's our preventative maintenance program. If there's a fault on the system with remote monitoring, we receive through our call center in 40 seconds an alarm identifies the site, the serial number of the turbine, and the fault code. We can tag in remotely, wake it up, and restart it, or load software. If we can't, we dispatch. So again, the 9-year FTP includes an engine overhaul. We have programs out to 15 years. Next slide, please. So I think some of the benefits and the drivers for our air-cooled, air-lubricated microturbine is that they are just that. They're air-cooled and air-lubricated. So we shut them down maybe 2 to 3 hours a year for maintenance. Again, it's only the unit needs to be surfaced. They offer very, very low emissions. Our current product is 9 ppm, which is what PSECU has. They have the ability to get down to 5 ppm on NOx, so extremely environmentally friendly. A benefit to having multiple 200s inside the container is this one it's a C800, so it's got 4 individual C200s. It's expandable to 5 without any additional real estate. And the inherent, and it provides, the multiple engines provide inherent redundancy, and the redundancy allows for maintenance to be done without interrupting power generation or thermal generation. Next slide, please. The controller for the system is a PLC-based controller developed by Capstone and Efinity. It provides real-time energy data and production and allows the PSECU to see the information and anyone remotely to see the information. It also acts as the backbone between the multiple turbines. It allows us to remotely change it from thermal priority to electrical priority. It'll always shut down the turbine with the highest run hours when the demand on the site is not high enough to run all 4. And the next time that sequence occurs, it'll shut an opposite engine down. So very robust and allows us to even out the runtime on the turbines. It diagnoses and troubleshoots 24/7, so it really becomes our hook with our online connectivity, allowing us to minimize downtime and maximize uptime for the end user. Next slide, please. So in closing, the final numbers at PSECU, gold status, 8 points. It's an 800 kilowatt gross electrical capacity, 4.25 MBH of thermal output hot water, 250 tons of chilled water, and the carbon reduction you see is just there. CHP does that for customers all the time. And I will say that the company, through Pete Spicer and Alan, are committed to demonstrating the value of the plant. They show the site regularly, and they've done everything to create a great project out there at the PSECU. Next slide. And I think that's the wrap-up. Thanks for your time, folks.
Hey, Jeff, thanks very much. That was a great presentation. I hope you didn't feel too rushed because you had great slides. And thanks also to Diane and Doug and Charlie. So we got some questions coming in here now. We've got one for Charlie Goff. It says, how can we meet the minimum energy performance prerequisite with the parasitic loads of a CHP versus a baseline non-CHP building if you are only building a central plant? So take it away, Charlie.
Okay, so first, for those people who aren't aware, in my presentation I mentioned how you start earning points once you exceed 10% energy cost savings. All projects are actually required to achieve 10% energy cost savings for their design building. So that's what's referred to as the minimum energy performance prerequisite. With respect to the central plant, from what I've seen and heard, that getting the central plant only certified can be difficult because the central plant doesn't really have a large load compared to the energy that it's producing. It's really exporting a lot of the energy to outside buildings. There is a district energy methodology that USGBC has developed to account for CHP energy that comes from a central plant that goes to outside buildings, but it's really a way to help certify those outside buildings. And again, from what I've seen, it's just the nature of how the central plant as a standalone building operates. It can be difficult to certify, but that's not to say it hasn't been done. But I guess that's all I could say about that question.
Okay, thank you, Charlie. We have a question for Diane here, and I think also Doug or Jeff, also you can weigh in here if you know the answer. And the question is, do you know of installations where the building officials fire life safety plans examiners have allowed CHP to power features required to operate during a power outage instead of on-site fuel storage power generators. Any volunteers?
I'll take that. Life safety usually requires either a liquid fuel or a dual fuel aspect in my knowledge. Okay, so a straight natural gas CHP system would not be allowed to fire the fire pump. I could be wrong, okay, but that's generally the response that I'm aware of.
Okay, thank you, Jeff. Anybody else want to weigh in on that? Okay. Diane, I have a question for you. What are sole source vendors?
When I say sole source vendors, I mean sole source accountability vendors, in that a company like Aegis takes charge of the CHP installation from engineering all the way through to manufacturing, installing, and maintaining, as opposed to there are vendors out there that just sell other people's equipment at an arm's length transaction. So when our experience has shown that we typically, our clients prefer to have someone who is a single point of responsibility. Does that make sense?
Okay, thank you, Diane. I've got one for you, Charles. Oh, did you have something to add, somebody? Sorry. Charlie, I've got one for you. What are GSA's LEED requirements for new buildings it plans to lease?
I believe that the requirement now is that for new construction and substantial renovation of federally owned facilities, GSA requires LEED Gold certification.
Okay. Let's see. We've got some more here. Here is one. I guess Jeff or Diane, either of you could take this one. Does the CHP system properly sized for the thermal load for commercial buildings typically export power to the grid?
No, they do not, because it's sized to meet the thermal load. Typically, as in the two case studies that I presented, the amount of electricity that's supplied by the CHP is considerably low, and therefore rarely is there any excess electricity. The system will shut down when that happens.
Yeah, no, let me follow on there. At PSECU, they are getting the benefit of net metering, and because the turbines can spool up and down depending upon thermal need, Pete Spicer actually, the last time I showed the site, was exporting 150 kW to the grid. So whether it actually got on the grid or is just net metering, at PSECU, they in fact are benefiting from net metering.
Great, thank you. I've got another question, Jeff, for you. Do you have any other LEED certified projects?
Was that to me, Jeff Biter?
Yeah, Jeff, yes.
Yes, we do. With our smaller C65s, we have one in Newark, New Jersey, a great little project. We have the NRU facility in Reston, Virginia, and Perkins and Wills in Atlanta, Georgia. So yeah, there's a couple of them out there. And again, the value of CHP lies in the ability to provide your own autonomous energy and thermal energy source inside your fence and not rely 100% on the grid. And I think that most people in the LEED environment and otherwise are starting to see the benefit of on-site combined heat and power.
Okay, thank you. So here's another one. What is the life cycle in years for these systems?
So let me speak to the reciprocating engines. Typically, the engines are changed out every 3 to 4 years, but really with proper maintenance, and as I said, Aegis has a maintenance contract with their clients. These systems really have an endless life. We have systems still in operation from the 80s, delivering energy savings to their sites.
Yeah, and I would agree with that. Normally, from my point, from Capstone, we obviously give it, say, 30 years at least, but we're all electronically components, so, you know, endless is I say 30 years, endless is probably achievable.
Okay, I think we've got time for one more question. What are the typical paybacks for CHP systems? And again, this would be, I think, Charlie, Diane, Jeff, you could all take a swing at this one.
I guess it depends. I'm sorry.
Go ahead, Jeff. Go ahead, Jeff. Go ahead.
So I guess it depends on the spark spread, the cost of electricity versus the cost of the burner to gas, as well as any incentive that you can get. So really, I've seen paybacks between 2 years and 10 years. I've seen customers take paybacks in the 6-year range. But, I'm sure Diane or others have, a great spark spread and see very, very aggressive returns. Again, are you displacing steam on a steam loop at a very high MMBTH cost? Do you have an incentive like in NYSERDA? So all of that matters. Go ahead.
Okay, Diane, go ahead.
Yes, so we've had the same experience. What we've noticed over the last few years is that developers are willing to take longer paybacks than in the past, primarily because of the low interest rate environment we're in. But they, in the past, we had to do projects that were in the 3 to 5 year range, and now they're actually can take 5 to 7, up to 9 years payback. But it really does depend on the spark spread, as well as the incentives, of which there are many, as I showed in a previous slide.
Okay, well, we got one more, and I think I'll try and take it, and then we'll wrap up. There's a question about, is there any way to earn innovation credits under LEED with a CHP system? And the only way I know is if you exceed the 50% energy cost savings requirement by a substantial amount. I don't know how much it is. I think there's an innovation credit for that, but that would be very, very hard to do. So anyway, I'd like to thank the audience for coming and for your attention and for your questions, and I'd like to thank all the panelists. And so we'll wrap it up, and good afternoon, and thank you, everyone. Goodbye.